Well, so this is the second installment of Industrial Engineering's seminar series in fall 2021. This week we have someone who recently joined our department. We are happy to have Oktay KARABAağ today presenting some of his research on integrated optimization of maintenance, interventions, and spare parts selection for a partially observable multi-component system.
What a long title, right?
Yes, it's a mouthful. It's a mouthful. We know Oktay for a long time. He recently joined the department, but he actually holds a Bachelor of Science degree from Statistics at Ege University, and then a master's degree in Intelligent Production Systems from İzmir University of Economics, after which he attended Koç University for his PhD, working under supervision of Professor Dr. Barış Tan, and thereafter he worked as a postdoc at Eindhoven University of Technology, and an assistant professor at most recently at Erasmus University's Econometric Department. Oktay, thank you for sharing your research with us, and the floor is yours.
Hocam, thank you for having me today as a speaker. Today I will be presenting one of my recent works, which is entitled as Integrated Optimization of Maintenance Interventions and Spare Part Selections for a Partially Observable Multi-Component System. Before getting to details of study, I would like to mention about myself briefly and what I have done so far. So, as Mahmut Ali Hoca mentioned that, so I got my bachelor and master degrees in İzmir. And then in 2018, I complete my doctoral studies at Koç University under the supervision of Professor Barış Tan. And right after that, I got an acceptance from Eindhoven University of Technology to work there as a postdoctoral researcher, and I have spent almost for 1.5 years over there. And then I went to Erasmus University Rotterdam, and I have served as an assistant professor at that university for almost 2 years. And at the end, I found myself at Yaşar University. So far, I have worked on different research projects actually. So during my doctoral studies, I mainly work on the procurement problems of manufacturers. So basically, my PhD dissertation includes 3 different essays. So in the first essay, in this one, we developed a stochastic model of a supply chain consisting of a set of buyers, suppliers, and the GPO. And by using this model, we analyze the effects of the existence of a GPO on the performances of all parties in the supply chain. And basically, in the second one, we collect an extensive data set from a group purchasing organization in Turkey, and we empirically analyze this data set to determine the main drivers that affect the buyer surplus in e-auctions. In the third essay, what we did, we studied the optimal purchasing, production, and sales strategies for a production system with limited capacity and fluctuating sales and purchasing prices. So currently, I'm collaborating with Burak Gökgür from Sabancı University to extend this study to cover dynamic pricing strategies as well. Basically, this work comes from my master's studies. So in this work, we develop a forecasting method which is capable of dealing with more than one calendar effect. And during my postdoctoral studies, I mainly work on the maintenance problems. So in this study, we develop a POMDP model to study an integrated maintenance and spare part selection decision for partial observable multi-component systems. So currently, I have 3 ongoing research projects. So I have already discussed what we are doing in this one. So the first ongoing project is related to the analysis of customer returns in the retailing sector. And the last one is related to the optimization of sales and production rollover strategies under stochastic demand and random yield. Unfortunately, none of these studies are ready for presentation yet. So therefore, today I will be presenting a work coming from my postdoctoral studies. So let me start by discussing the motivations that drive us to conduct this research. So as you know, many operations in public and industrial organizations heavily depend on the functioning of large and technically complex machines. So examples may include lithography machines in the semiconductor industry, or medical imaging machines at hospitals, or radar systems on vessels. So typically, unexpected downtime of these kinds of machines can lead to a significant loss of revenue and also can negatively affect safety, health, and the environment. So basically, CBM, I mean, condition-based maintenance, is introduced as one solution for reducing these kinds of risks. So essentially, CBM is a maintenance policy that finds an optimal maintenance moment to minimize the overall maintenance cost based on condition monitoring information, such as vibration, temperature, or power consumption. So as you can understand from this definition, the implementation of this policy and its performance depend on the monitoring and the analysis of the system condition data being obtained through a condition monitoring instrument, I mean a sensor. However, in practice, the sensors being used for this purpose are not perfect. So what I mean by that, so it may not be technically or economically possible to observe the exact condition of each component in a system with these sensors. But on the other hand, they could still provide us some partial information on the system condition. Of course, having partial information on the system condition makes the maintenance problems of multi-component systems further complex. Because as a service provider, you should not only decide on when to perform a maintenance intervention, but you should also decide on which spare parts to bring to the customer place when you decide to perform a maintenance intervention. So basically, in this study, we are focusing on this challenging problem. So here, I mean, in this work, our aim is to study an integrated maintenance and spare part selection decision for partial observable deteriorating multi-component systems, and to explain how system characteristics affect the value of having full information on the component saturation levels and the value of using the optimal policy compared to two slightly naive policies. So I will introduce the details of these naive policies in my following slides. Okay, so in this context, what we did, we considered three different research questions. So the first one is, what are the optimal maintenance and spare part selection decisions for a partial observable multi-component system? And what is the value of having full information on the component saturation levels? And the third one is, what is the value of using the optimal policy compared to a corrective and the preventive maintenance policies? Okay, so what we did, as a next step, we conduct an extensive literature review to better emphasize our contributions. So in the literature, we have found a number of studies employing the stochastic models to study the maintenance problems of single component systems and multi-component systems. So we also noticed that none of these studies considers the spare part selection decision within the condition-based maintenance context. So I think I can say that. So we are the first study to focus on this challenging problem in the literature. So therefore, the novelty of this work stems from the inclusion of the spare part selection decision in the condition-based maintenance optimization problem. Okay, so let me give you our problem description. So here we consider that a system, a system that consists of n critical components. And the system is operational as long as all critical components are functioning. So the components are subject to deterioration during the time that the system is operating. And the deterioration process of each component evolves according to a discrete time, discrete state space Markov chain. So for each component, we consider that there exists a predefined defect level delta and predefined failure level F. So let's consider component I. If the deterioration level of component I is strictly less than its corresponding defect level, then the component is referred to as non-defective. So if the deterioration level of component I is somewhere between these two bounds, I mean delta I and Fi minus 1, then the component is referred to as defective. And if its deterioration level equals its failure level Fi, then the component is referred to as failed component, and it is not functioning anymore. So in the system, we consider that there exists a single sensor. And with this sensor, it is only possible to observe whether there exists at least one defective or at least one failed component in the system. So what I mean by that, if there exists at least one failed component in the system, then we will receive a red signal or a failure signal from this sensor. So if there exists at least one defective component and no failed component in the system, then we will receive a defective, I mean a yellow signal. So in case of no defective, no failed component in the system, then we will receive a green, I mean a non-defective signal. So here I should again note that the exact state of the components cannot be observed with this sensor. So they can be observed only through a complete and perfect inspection. So the service provider is only able to observe these sensors. So he or she is not able to observe the core system, core states. Okay, so as the service provider cannot observe what the exact iteration level of each component is, she introduces a belief state to find the maintenance intervention moments. So basically in this sense, the belief state can be considered as a probability measure to estimate the exact state of the components. And the sequence of events in each period can be depicted as in this picture. So let me try to clarify this picture for you. At the beginning of each period, the service provider receives a signal from the sensor, and based on this signal, she updates her belief states. If she receives a red signal, then she immediately performs a corrective maintenance intervention, and she pays a fixed corrective maintenance cost for that action. So if she receives either a yellow or a green signal, then she has two options. She either does nothing or she performs a preventive maintenance intervention. So in case of no maintenance intervention, of course, she pays nothing. But in case of a preventive maintenance intervention, she pays a fixed preventive maintenance cost. Okay, so when she performs a maintenance intervention, she is able to observe the exact condition of each component in the system, and she replaces each failed and defective component with a new one. So for each replacement, she pays a fixed replacement cost. On the other hand, when she decides to perform a maintenance intervention, she should also decide on which spare parts to bring to the customer place. So if a component has not been brought to the maintenance place, but needs to be used in the maintenance, then she brings it to the customer place by using an emergency order procedure. And she pays a fixed emergency order cost for that particular item. So if a component has been brought to the maintenance place, but not used in the maintenance, then she brings it back to use it in the other maintenance interventions, and she pays a fixed return cost for that particular item. So under this setting, the service provider seeks to find the optimal maintenance and spare part selection decisions that minimize her expected total discounted cost over an infinite time horizon. Okay, so let me give you the details of our mathematical model. So here we model the system as an infinite horizon partial observable Markov decision process. So in this model, the set of core states is denoted by this fancy S. Basically, it covers all the possible states that the system can be in. So here we consider that the components iterate according to a discrete time, discrete state space Markov chain whose transition matrix is Q. And the element in this Q matrix, I mean QSS prime, denotes the one-step transition probability from state S to S prime. So the possible outcomes coming from the sensor are denoted by theta, and the element of this set, I mean 0, 1, 2, denote non-defective, defective, and failure signals. So here, our sensor works perfectly, and therefore we are able to write our core states as in these three disjoint sets. Okay, so the belief state in our model, the belief state is denoted by pi, and basically it composes the state space of our problem. So in this vector, pi I denotes the probability of being in state I. So here you can see the actions that the service provider can take. The first one is related to her maintenance actions. So as I mentioned before, in case of a red signal, she has only one option. She immediately performs a maintenance intervention. So in case of a green or yellow signal, she has two options. She either does nothing or she performs a maintenance intervention. So the spare part selection decision is denoted by this binary vector G. And when the service provider decides to take the component I, then GI will be 1. So otherwise it will be 0. So here you can see the costs that the service provider needs to take care of. The first part is related to her maintenance decisions, and the second one is related to her spare part selection decision, actually. So as I mentioned before, in case of a corrective maintenance decision, intervention, then she pays a fixed corrective maintenance cost. And in case of a preventive maintenance intervention, she pays a fixed preventive maintenance cost. So here, the first one denotes the replacement cost. The second one denotes the return cost, and the last one, this one denotes the emergency order cost. Okay, so what we did as a next step, we introduced two different operators to define a value function. So the first one actually denotes the action of not performing a maintenance intervention. And the second one denotes the action of performing a maintenance intervention. So basically, by using these two operators, we define our value function as in this equation. So here, our aim is to find the optimal A, the optimal maintenance and spare part selection decision that minimize this value function. Okay, so it is time to discuss the numerical analysis or our numerical results. But before giving those details, I would like to mention about our experiment setting. So here we utilize a grid-based solution algorithm to find the optimal policies for our problem. And in this study, we considered 3 benchmark policies: full information policy, preventive policy, and corrective policy. So under full information policy, we consider that the service provider is able to observe the exact condition of each component in the system. So basically, she is able to observe everything in this policy, under this policy. So under preventive policy, the service provider performs whenever she receives a yellow signal. She is really, under this policy, she is really sensitive to receiving yellow signals or defective signals. So under corrective policy, the service provider performs, maintenance interventions only upon receiving a red signal, a failure signal. So otherwise she does nothing. We also introduced 2 different performance indicators to assess the value of having full information and the value of using the optimal policy compared to these 2 naive policies, actually, preventive and corrective policies. So as you can understand from the definition of these performance indicators, the hierarchy means the higher the value of having full information and the higher the value of using the optimal policy. Okay, so in our numerical instances, we divide our parameters into 2 subgroups, invariant and variant ones. So here you can see the set of invariant parameters. In all numerical instances, we consider a system with 2 components, and the failure levels of these components are set to 3. And the preventive maintenance and return costs are set to 130 respectively. And our discount rate is set to, we set the discount rate to 0.95. So here, So for corrective maintenance cost, emergency order cost, defect levels, replacement cost, and the transition matrices, we consider different alternatives. So by using these alternatives, here we utilize a full factorial experiment setting. So by using this full factorial experiment setting, we generate 3,240 different problems or different instances. So by using these problem instances, we get the following results. So in this table, you can see the results related to the effects of corrective maintenance cost on the system. So basically, in this table, we observe that with an increase in the corrective maintenance cost, the benefit of using the optimal policy compared to corrective policy increases, whereas the benefit of optimal policy compared to preventive policy decreases. So this table also shows that as the corrective maintenance cost increases, the positive impact of having full information increases. Because in this case, having more information on the component's iteration levels would help the service provider to exploit each component's lifetime and maintain them just in time. So therefore, the value of having full information increases at this point. So here, this table summarizes the results, this table shows the effects of emergency order cost on the system. Here we observe that with an increase in the emergency order cost, the benefit of using optimal policy compared to corrective policy decreases, whereas the benefit of using optimal policy compared to preventive policy increases. So when the emergency order cost is high, the service provider performs maintenance interventions whenever she is almost sure about the component status. So basically, with this strategy, the service provider avoids paying high emergency order costs due to ineffective spare part selection decisions. So, as a result of this strategy, the optimal policy starts resembling to corrective policy, and therefore the cost difference between these two policies starts decreasing. And the same reason leads to an increase in the cost difference between the optimal and the preventive policy. Okay, so here we also notice that the benefit of having full information increases as the emergency order cost increases. So basically, at this point, having more information on the component's iteration levels would help the service provider to improve her spare part selection decisions and to avoid paying high emergency order costs. So therefore, the value of having full information increases at this point. Okay, so here, this table basically shows the effects of the transition matrices on the system. Here we notice that with an increase in the difference between the components' iteration rates, the benefit of using the optimal policy compared to corrective policy increases, whereas the benefit of using the optimal policy compared to preventive policy decreases. So let me try to explain the reasoning behind this result. Actually, when the difference between the components' iteration rates increases, the risk of going into a failure state after observing a yellow signal increases. So basically, the service provider avoids this risk by performing preventive maintenance interventions in early defective states. So therefore, the optimal policy starts resembling to preventive policy again. So the cost difference between these two policies starts decreasing. And the same reason leads to an increase in the cost difference between the optimal and corrective policies. So here we also notice that the benefit of having full information increases first and then decreases as the difference between the components' iteration rates increases. So let me try to clarify or explain the reasoning behind this pattern or result again. So suppose that we have two components and they have similar characteristics, similar iteration characteristics. So in this case, they are likely to fail or defect together in the same period. Actually, this helps the service provider to perform joint maintenance interventions. And therefore, she is able to save on the maintenance cost a lot. On the other hand, she has no difficulties in selecting the correct spare parts because she knows that both components are likely to fail or defect together in the same period. So whenever she decides to perform a maintenance intervention, she brings both components to the customer place. Okay, so suppose that the difference increases slightly. So in that case, the likelihood of performing joint maintenance interventions decreases. And on the other hand, the risk of bringing the wrong component to the customer place increases. So to avoid these risks or to reduce these risks, the service provider needs more information on the components' iteration levels. So therefore, at this point, the value of having full information increases. Okay, so suppose that the difference increases considerably. So in that case, performing joint maintenance intervention is not likely anymore. And due to this fact, there will be no much room to improve it. And on the other hand, she would have no difficulties in selecting the correct spare parts because she knows that the unreliable component is the main reason for performing these maintenance interventions. So whenever she decides to perform a maintenance intervention, she brings that component, I mean the component for the unreliable one, to the customer place. So therefore, at this point, the value of having full information starts decreasing. Okay, so let me conclude my presentation. So here we observe that the service provider needs less information to manage the system effectively when the component situation characteristics are very similar to significantly different from each other. And having a condition-based maintenance program will be of value to practitioners when the corrective maintenance cost gets higher. So of course, we have a couple of limitations in this study. So as you may notice in this presentation, we do not characterize the optimal policies analytically because characterizing them analytically is really a tough task. I mean, we're not able to do that. Therefore, characterizing them analytically would be a great idea for future research. And again, in this presentation, you may notice that we only consider a small system. I mean, a system with only 2 components, because the solution method that we use in this study was struggling due to the curse of dimensionality. So therefore, developing an efficient heuristic algorithm that can deal with larger problem settings would be a great idea for future research. So in this sense, I'm planning to use some machine learning or AI algorithms to deal with, let's say, larger problem settings. And here, I mean, in this study, we do not consider inventory decision, and also we do not optimize the replacement decision, because when you try to incorporate these decisions into the current version of the problem, then the state space explodes.
Oktay, I'm very sorry. I have to make an announcement. You maybe see all this message that it might end. I called up about 10 minutes ago when it first appeared. People who's in charge, they're trying to do that, but if it ends, I really don't know what to do. But you know, okay. I'm sorry, just go ahead so that you know.
Okay, Hocam. So let me repeat myself again. So here, I mean, in the current version, we do not consider the inventory decision, and also we do not optimize the placement decision. Because when you try to incorporate these decisions into the current version of the problem, the state space just explodes. Therefore, we do not consider these 2 decisions in the current version of the problem. So maybe also incorporating these decisions would be also a great idea for future research. But I think it would be valuable if you are able to make the second one. Because otherwise, most probably we will not be able to solve the problem again. So thanks for listening to me, and any questions?
Okay, dear Oktay, thank you for the presentation. That was we had a little hitch at the end, but hopefully next times we'll be more careful. I'd like to open up the floor for questions right now from our audience. Because I have a very theoretical question that I'd like to ask, but maybe first say, Oktay, can you go to the beginning of your presentation? That is because there's something very wrong. Very beginning, please. Okay, who the hell is that guy?
Hocam, you should have a good look at this picture, because this is the first and last time you see me without beer. So.
Okay. I'm so sorry. Okay, now let's take some more serious questions.
Hocam, I have a question.
Yes. Yeah, yes, please go ahead.
Oktay, thank you so much for the presentation. This is a nice MDP model. Could you please open the slides? I don't know, I don't remember the number of the slides, but okay, this one.
This one?
Yes, yes.
Okay.
This one. The real system.
Hocam, the real system is this guy.
Is the one on the left part, right? But what the controller observes is the right part, right? Right part.
Yeah, exactly.
Defective, failure, and we actually, do we know the real Markovian process of the left part? Do we know?
We assume that in the model we know that. We know the transition matrices for these core states.
We know the transition matrix, but we do not know the exact state, right?
Exactly. So if you are a service provider, so you are not able to observe the core states, but you know the dynamics of them, MDP dynamics of them. Okay.
Then suppose we observe the yellow signal, right? We observe that there is a defective item somewhere in the real system.
Exactly.
Under this information, as a conditional distribution, is it possible to calculate the probabilities of the components to be in the failure state or defective state?
Hocam,
we know the dynamics, right?
Hocam, here we assume that our sensor works perfectly.
Okay.
So therefore, it is not possible to have, let's say, a red signal when we are in defective states.
No. Let's stick into the defective state. We observe that there is a defective item in the system, right?
Okay.
Okay. And since we know the dynamics of the real system, I think we can calculate the probabilities of the components being in the defective state, right?
Hocam, by using actually those belief states, we are doing this. So in the belief states,
you are doing the same thing. You are doing the same thing. Yeah. Okay. So it is an integral part of your MDP formulation. What I am trying to ask is, okay, this is a very nice MDP model at practice, but can we solve this problem without using Markov decision processes? Because we know the dynamics, and under the additional information of being in defective state, failure state, non-defective state, I think we can exactly calculate the probabilities corresponding to the components, right? Because you know the dynamics, how they evolve within time, how they change their states. So based on that probabilities, we can also calculate the expected cost of actions, and we can select.
In that case, how are we going to update our belief state? Here we need to have an input.
With the signal, okay, we are going to have the input. The input will be either failure, red, defective, and non-defective.
Okay, so those are the signals.
Under this input signal, forget about the MTP, because then calculate everything as a stochastic process where the dynamics are known. Just calculate the probability distribution of the components, the states of the components, recalculate them under the new information, calculate the expected cost of actions. Can it be done?
But I think in that case, that will be similar to what we are doing here, right? Because here what we are doing, at each period, we are receiving a signal from the sensor. And based on that signal, we update our belief states. So basically, what I mean by that, so we update the probabilities of being in a particular state. Okay,
then that stage might be enough. If you put this information to an MDP configuration, then you need to iteratively solve it, right? What I am trying to say is, okay, calculate all these, then calculate the expected costs of the actions, theoretically, analytically. Okay, maybe we can obtain some analytical results and write an optimization function or optimization problem, develop an optimization model, classical optimization model for that calculation. That's what I am trying to say.
Hocam, I have never thought about that option. but
because if the dynamics are known, I think we can recalculate the distribution, the mean distribution under the additional information given by the signal, the three of the signals, right? And then analytically, I can write the codes based on the decision variables, make the actions as the decision variables of a classical optimization problem.
Hocam, but in that case, what will be your state space? I mean,
so you know what I understand, these are not the true system states, right? These are just the
What we observe.
sensor,
Yeah.
you know, indicators from sensors. These are not the true system states.
Yeah, but,
exactly, hocam.
but we using these indicators, the sensors, the information gained
To
by the
estimate
sensors,
the
we can estimate the probability distribution of the real system.
yep.
And then write the expected cost of every decision. Okay.
That's a good point, hocam, but I have never thought about that. So maybe we can discuss this in detail after this presentation.
I don't know whether it works or not, just an idea.
But if it works, it will make everything really easy. So instead of dealing with that complex or sophisticated solution method,
Yeah.
then
And
maybe we can use that guy.
Okay. Okay, maybe. I don't know. Okay, thank you.
You're welcome, hocam.
Yeah.
Well, I have something to continue with on that point. Do you have somewhere, you know, false negative or false positive indicator?
No. Here, hocam, we assume that our sensor works perfectly. So therefore, we are able to write our core states in these three disjoint sets. So if we are in one of those yellow states, then we definitely receive a defective signal. So it is not possible to, for instance, get a failure or a green signal when you are in these yellow states, actually.
Okay, then Önder's point is quite legitimate, I believe. Yeah.
Okay. So as I told you, hocam, so I have never thought about that option, but that might be really helpful because the current solution method we are using the solution method we are using in this study really is struggling due to the curse of dimensionality. So maybe we can use that idea to deal with larger settings.
Okay.
That's a good point, hocam. Teşekkür ederim. Thanks a lot.
Ne demek?
Teşekkür ederim.
Well, how do you solve, you know, how do you obtain your numerical results now? You know,
Hocam,
solve this?
Hocam, in this study, we are using a grid-based solution algorithm. So we have some grid points, and at those grid points, we are calculating our value function. And based on that calculation, we are finding our optimal solution. Actually, in this study, Sena took that part. I was doing the modeling part. So this is, I know only the basics related to the solution algorithm, to be honest.
Okay, so you are basically doing a search for all possible points, right? So this is a greedy algorithm, you know. Okay.
Okay. Any other questions, maybe?
As a continuation of Özgür Hoca's question, can I ask how do you define a grid, Oktay, in this grid space?
Hocam, it's a user specific procedure. So you can define as many grid points as you want. But in our case, as far as I remember, we were using like 20 grid points or so. And I mean, the grid points basically corresponds to the probabilities in the belief states, actually. So it depends on you. I mean, it's a user-specific parameter.
I'm trying to understand why do you name it as grid-based algorithm?
So we didn't develop that method, hocam. It was in the literature. So we just use that existing solution method actually. So they call it as a grid-based solution algorithm.
Okay, thank you.
Oktay, to be discussed further later, but can I ask you if so you are trying to minimize some sort of expected cost of service provider, right? And at the beginning of the presentation, you said this problem particularly applies to where you have medical imaging devices or that semiconductor printers. These are things that we want to be highly utilized. They're expensive. They're in fewer places, but we want them to be highly utilized. So there's, I think you can modify it probably, but there is nothing here from the perspective of this is not an optimization. From the perspective of keeping the operational uptime to a maximum. So this is the cost of the service provider. You're looking from the point of view of a service provider, but in the end, these agreements are either made including some sort of operational objective. So you're not looking up how much you're trying to keep this up. For example, there's nothing related with those kind of things. It might be an easy, let's say, adaptation. I don't know really, but I think it is as much interesting, at least, to have some sort of make the objective from the point of view of the user, actually, because those are the things. Sometimes even these machines are leased, or people would want to keep them highly utilized. So I think that is something to think about.
Hocam, there's a really interesting point. So I think you are totally right. So this could be an extension of this study as well. I mean. We can even consider it as a constraint in our mathematical model, or we can consider it as another objective here. In that case, we will have multiple objective problem. But that's a really interesting point.
Yeah, either one of those either comes as a constraint on the how much you keep it up or how fast you keep it up, or becomes an objective function as well. But okay, thank you. I have a couple of more things, but I don't like fuzzy, so I'm not going to get into this. The classification of not working or working here is so strict, right? So up until how you describe it is that goes, and a certain state it's not working. That's very difficult to determine where, right? Okay, so okay. Anyway, thank you. And that's all I have.
You're welcome, Hocam.
Okay, any other questions from the audience? Well, if not, we are lucky that we can see Oktay almost all the time. And if anything else comes up, we can discuss later on as well. At this point, I'm going to end this installment of the seminar series. Thanks, everyone, for attending. Thank you, Oktay, for presenting. Thanks, Önder Hoca, Özgür Hoca, for their contributions. And we'll see you all in our next installment 2 weeks later from now, hopefully with Özgür Akgün as our guest from Seminerleri University's Computer Science Department.
Thank you. Thank you, Oktay. Bye-bye.
You're welcome.
Bye.
Bye, everyone.